Welcome back, students. Welcome back, students and others. Let's take a look at sound waves and how to digitize them. Okay, I thank Daryl Lonsdale as well as Brian Anderson in the physics department here at BYU for some of the slides that I have here. First, let's talk about the physics of sound a bit. But before that, let's talk about the physics of water, because it's probably a little easier for us to see water or think about water. So here's an image. By the way, all my images, I give the link in the notes to each slide if you'd like to look at where exactly I got these images. We have several things I want to point out here. Number one, we have up and down, right? They're using the word crest and trough here. I'll probably use the word peak and valley. In technical terms, the peak is called condensation, if I'm not mistaken, or compression. Also, I've heard that term. And the valley is rarefaction, to use a very technical term, right? So it's this kind of pressure, kind of oscillating back and forth pressure at some point. So let's talk about a couple things here. The dotted line across there is the still water level. I might use the word origin for that kind of standing still level where there's no wave. And then the crest, like I said, I'll use peak or compression or condensation. And the valley, So the wave height there is the amplitude. The word amplitude refers to the wave height. We'll see in a second when we go to talk about sounds, that's loudness. That's the volume that you hear. The bigger the wave, the bigger the height or the amplitude, the louder the sound will seem. And then the wavelength here is from one peak to the next. So this right here, wavelength, or from one valley to the next, doesn't really matter exactly where you measure it, as long as you're doing it consistently from either a peak to a peak, or valley to valley, or from the midpoint where it crosses the origin to the next wave over there where it crosses the origin. It's all the same, right? That's the wavelength. And the closer those wavelengths are, the higher the pitch of the sound will be. Now we're looking at water here. I just wanted to start with water because you've probably seen water waves and you can visualize what's happening there. Very much the same thing with sounds. So what is a sound? Well, it's simply variations in pressure through some medium, usually air, and it can be through liquid, as you know, you can hear underwater, or through a solid, where it can transmit through a wood, like a wood door or metal door. Okay, so what is sound? Well, it involves production, transmission, and reception. There's different sources of production, right? It could be a stereo speaker, a cell phone speaker. It could be the human articulatory apparatus, meaning the lungs coming up through the trachea, hitting the vocal folds, vibrating them, modifying that sound as it comes out of your mouth and or your nose. Like that whole thing is articulatory phonetics, right? A tuning fork, right, also gives you a clear or sine wave or a pure tone. Those are all synonymous. Pure tone, sine wave are produced by a tuning fork. And that's, I think, the only thing that I can think of that actually produces a pure tone or a sine wave or a sinusoidal wave. Sinusoidal. Those are all synonymous. Sine wave, sinusoidal wave, and pure tone. Okay, good. Right, so the medium can either reflect, or attenuate, or amplify the sounds. And there are two kind of fundamental elements to sound. One is pressure, that is how big the amplitude is on the wave, and then the time. Again, like I mentioned, the closer those waves are together in time, then and in physical distance, then the higher the frequency will be. And the farther they are apart, the longer the wavelength is, and therefore the lower the tone will be. So waves are simply a way of representing those sounds. There are two types of waves. Well, there's more than two types, but we'll mention two here. Longitudinal waves is when the molecules, like the particles, are moving in the same direction as the wave. And transverse is when they're moving opposite each other, meaning the particles are moving perpendicular to the way that the wave is moving. So let's take a look at some GIFs here. So here is a longitudinal wave. In the red, we have little individual particles, right? These could be air particles when we're talking about sound, air molecules. Okay, and so the wave is propagating or going through the air molecules. We have the wave in black there. right there, right? So these peaks are the compression or the condensation or just the peak, right? They're moving through, but each individual molecule is only moving a little bit, and it's moving in the same direction as the wave, so it's a longitudinal wave. And so when the compression comes, it kind of moves with it a bit, and then when the wave goes past that red point, that red particle, it kind of goes back a little bit. It's kind of being sucked back. So anyway, there is a longitudinal wave. This is what sound does. Here is a transverse wave, so each particle is moving perpendicular to the way the wave is moving. Right, so each particle is moving up and down vertically, but the wave is moving to our right. Okay, so those are the different types of waves. There are others, but these are the ones that we'll just mention here. And again, the longitudinal wave is the most important for us with sound. Let's talk about frequency and wavelength. Like I mentioned, wavelength is the distance between two waves, like two, either peaks or valleys or the origin point to the next origin point. That's called the wavelength. And so the closer they are on the top right of this slide, the closer they are together, the higher the frequency will be. And the lower that those peaks are to each other, like the farther apart they are, the lower the frequency will be. Okay, you can talk about the speed of waves. Air, sound waves move through air at about 340 meters per second is how fast sound waves move through air. And underwater, they actually move quicker, if I'm not mistaken. To double check that. But even the temperature of air can cause sound to move slower or quicker. Sound moves, is it hotter or colder? Let me think through that real quick. Shoot, I can't remember off the top of my head. Sound moves slower through, I can't remember off the top of my head. Anyway, so sound can move slower or quicker through a hot or cold air. So, okay. So hertz, the bottom left of this slide talks about hertz, and that's 1 cycle per second. And cycle, by the way, I'll either use cycle or period. It's one full wave, meaning like from peak to peak, or from the origin back to the origin, or from the valley up and back to the valley. That's one cycle or one period. And hertz is the unit of measurement to talk about how many cycles or periods there are in a second. So when you hear 440 hertz, someone says, oh, that sound was 440 hertz, like A4 on a piano, which is the A above middle C on the piano. There's 440 cycles or periods of that sound wave in 1 second. Okay. Anything else there? I'm going to jump over to a virtual piano real quick. We're going to go to a virtual piano just for fun. And we're going to play. Let me turn on the notes here. So A4, let me zoom in a bit. A4 right here. If you don't know the piano, that's all right. But this right here is middle C. This right here is A4, which is A above middle C. That is 440 hertz. And if we wanted to, we could actually test that. Let me just grab my old friend Pratt. Let me grab this window. My old friend Pratt. In fact, I've done this before the video started, but let's do it again. If I come into sound and create pure tone, create sound as pure tone, and then bring the window over here so you can see it. And I say I want 440 hertz. It says tone frequency HZ, that's hertz. 440 hertz. Let's give it, 0.5 Pascal there, and we'll call it A4. Oh, I need to put a 0 before that dot. It doesn't like that. Okay. If I play this, that's the same frequency as A4 right here on the piano. Middle C is at 261.6 hertz. Let's go create middle C with Pratt real quick. Sound, pure tone. Let's call this C4, which is the name for middle C. I change this to 261.6. Leave it at 0.5 Pascal, which is the amplitude, and play it. And there you have middle C. Yeah, so The frequency, like how quickly the waves are coming, is what determines the pitch. Okay, that was cool. All right, let's keep rolling here. Decibel scale. So humans, we can hear from about 20 hertz up to 20,000 hertz. That's our typical hearing range. Although the older you get, you kind of drop out in the upper range. You can't hear the upper ranges that much. In fact, I'll show you a little demo here in a minute. But elephants can hear below 20 hertz. And other animals like bats and dogs can hear up to dogs can hear up to 50,000 hertz. And bats can hear, I think, even higher up than that, over 20, even higher than 50,000 hertz. But you may know what dog whistles are, right? A dog whistle is a whistle that we humans don't hear because it's above our frequency, the amount of frequency that we can hear, but dogs can hear it. So that's why it bugs them, but doesn't really bug us. And then the decibel scale here is a log scale. I'll talk more about that in a couple slides. But you can measure how loud it is or how big the amplitude is. It's the amplitude of the wave. With fireworks, above 140, at 140 decibels, that is where your hearing hurts. You can feel your ears hurting at 140, or even perhaps above 120. A jet engine is at a 130 decibels. Police siren at 120. Trombone, you can see it kind of goes down. A hair dryer is at 90. A truck is very loud, etc. A whisper is at 30 decibels. And then 0 decibels is the weakest thing we can hear. 0 decibels is our bottom ability to hear. So we have two different things here. We have hertz, which is the frequency, which determines the pitch, the musical note, so to speak, of the sound. And we have loudness, which is measured on here a decibel scale. That's a sound pressure level scale. Pascal is a sound level scale. Okay. Pressure. Let's talk about pressure real quick. So pressure, a little math here, nothing big. We have force divided by area. So let's just look at the ballerina on the right-hand side of this. Let me remove myself for a second. If I come back over here and remove myself with this. We have a ballerina on the right-hand side of this slide. So when she is standing with both feet flat on the ground, let's say that the soles of her feet take up about 12 inches squared. And let's say she weighs 120 pounds. And so that creates a pressure of 10 pounds per square inch. But in case 2 on the bottom right of this slide, if she's on point, right on the tip of her toe, then the surface area that the tip of her toe, let's say, is taken up is about 3 inches squared. And we have the same weight, which is 120 pounds, pushing down on a smaller area, so the pressure is higher. It's at 40 pounds per square inch. Okay, so just to understand what pressure is, it's force, in this case weight, divided by area, but force can also be pressure of sound. So just want to start with that simple idea of pressure. Okay. And let's say we're on the surface of Earth, which I am, and we have molecules above us, air molecules, which creates pressure down here on Earth, on the crust of the Earth, right? At sea level or at 5,000 feet above sea level, whatever. So that weight, the gravitational force, is causing there to be pressure here, and there's more molecules closer to the ground than there are way above, way up high in the atmosphere. That's why, if you hike up a really tall mountain, you can get dizzy because there's less air pressure and there's less oxygen up there because there's less air up there generally. There's less pressure. Okay. So you can measure acoustic pressure with Pascal and decibel. Okay. And the airwaves cause deviations in the local air pressure. There's a kind of a constant air pressure, nothing's happening. But if I start talking, I'm causing the air to be perturbed or disturbed, to deviate, and those airwaves go to your ear, and you hear something. There are different units of measurement of pressure. Newtons, it's the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. Pascal is 1 Newton divided by, what is that, meter squared N. Cool. Decibel is a logarithmic scale. It's a sound pressure relative to a reference level. That reference level is 20 micropascals. 20 micropascals is 20 millionths of a pascal. Okay. So 1 pascal, I'll show you the formula here in a second, translates into about 94 decibels. And like I mentioned earlier, sound waves travel in air at about 340 meters per second. So this is how you convert between pascal and decibel. It's on a logarithm scale. You can see the dB, the top formula there, has that log 10. And so what happens there is that we hear in a logarithm way. That's what we have the log there. The bottom function there is how to get pascals from decibels. dB is decibels, PA is pascal. Okay, the point here is that pascals are the measure of sound pressure, and dBs or decibels is a measure of sound pressure level, and it's on a logarithm scale because of that log 10 right there in that formula. Okay, let's talk about intensity, another key concept in sound. Intensity is the pressure per area. And here is an example of how this happens with sound. Let's say we have a speaker on the left-hand side right there. We have a speaker that's playing something. And when you're it goes out in a sphere, right, from the sound source. It goes out in a sphere, like a globe, right, going out. And it doesn't go down linear. The intensity doesn't go down linearly. It goes down exponentially because of that formula right there. So it's 4 pi the radius squared. Because of that r squared there, the radius squared, rather than going down, say, like if you go twice as far away from the source, like if you're just 1 foot away versus 2 feet away, it's actually a fourth as loud 2 feet away than 1 foot away. So we try a little experiment? Why not? Let's try a little experiment. I'm going to put my microphone up here. You can see, yeah, I'm putting my microphone about a foot away. Probably about a foot away right now from the microphone. Let's say 1, 2, 3, 1 foot away. 1, 2, 3, 2 feet away. 1, 2, 3, about 3 feet away. 3, 4, 5, about 4 feet away. 5, 6, 7, 5 feet away. Anyway, you should have heard, obviously, that it goes down in intensity or volume. It should go down at an exponential rate, not just a linear rate, because of this concept right here that the sound has to go out and propagate in a sphere, not just a single line. It has to propagate out like that with that r squared and that formula there. So the take-home message is that sound goes down at an exponential rate the farther you get away from that sound. And so an application of this knowledge is that when you're recording someone, you want to make sure the microphone is as close to their mouth, to them, as possible. The best recordings, right, are those where the microphone is close as possible to the person who's speaking, or their mouth, really. Okay, so I have my microphone for this video right here, right off camera, right below, pointing up on, it's on my desk, pointing up. I'm about a foot, maybe 14 inches away. Anyway, okay, so that's intensity. Now let's talk about digitizing sounds. So we're trying to have a staircase mimic a hill. Now, what do I mean by that? As you know, on the right-hand side of the slide, I have a hill. And there are an infinite number of points on that hill that I could say, how high is it at this point? All right, let's say if I use my mouse here, I think you can see my mouse on my video. Right here, let's say I take a point right here, and that's, I don't know, whatever, 20 feet off the meadow, off of the grass there. And I take a point up here, and that's maybe 40 feet there, and maybe the 60 feet. There are an infinite number of points that I could take, right, on that hill to figure out its height over time, from left to right, that is, at least, from left to right. But we can't take an infinite number of samples because the computer would fill up, you just can't do that. You can't take an infinite number of samples of a sound. A sound wave has an infinite number of points along its peaks and valleys that you could sample, but you can't do that. You have to just take discrete samples here, here, here. And so the staircase I use here, as in this metaphor, this analogy is each stair on that staircase is a sample, a specific time point where we're saying, okay, what's your amplitude here? And what time are you at? Okay, I'm going to take another one here. Where are you at here? And now here. And so that's the idea where the sound wave is like a hill, and we have to figure out how often we want to take a sample or take a little stair step is the idea that I'm trying to get across there with this idea with a staircase and a hill. Right, so we have an infinite number of points. Good, we have to sample them. And so like I mentioned, 1 hertz or 1 Hz is 1 sample per second. That's not going to be useful for actually faithfully capturing sound. CD quality has 400 or 44,100 hertz per second. I mean, every second it's taken 44,100 samples per second. So when that came out, I don't know how many years ago now, 30 plus years ago when CDs came out, they were the cat's pajamas, right? Because they had such a high quality sound because of this very thing. They were taking a lot of samples. Cassette tapes, the precursor, right? My mixtape back in the 80s only had 14.5 thousand samples per second. AM radios at about 22,000 hertz or 22,000 samples per second. Telephones are down at about 8,000 samples per second. That's why it sounds bad. I mean, telephone conversations, right, don't sound good. Like if you ever had someone like try and play you some music over the phone, like, hey, listen to this, man. It doesn't sound good at all because it cuts down the quality of the audio because it has so few samples, only 8,000 per second. Great. So that's the idea with digital sampling. And how much storage does sampling take on my computer? Well, it depends on several things. It depends on your sampling rate or your frequency of sampling. It depends on how many bits you're using per sample. Meaning if I have 44,100 samples per second, how many bits on the computer are each of those samples being stored with? And then the number of channels. I mean, do you have stereo? Stereo has 2 channels, mono has 1 channel. That also affects what's called the bit rate. The bit rate is how many bits or how many zeros or ones are being used for each second to store a sound. And then you take those, the number of bits, and you times it by the number of seconds of your sound. And then to convert bits to bytes, you take the number of bits and divide it by 8, that middle function there, or that middle formula. And then to convert from bytes with the Y to kilobytes, you divide it by 1024. I do not know why it's not 1000. And then to get megabytes, you divide the kilobytes by 1024 as well. So, for example, let's take an example here. So a telephone line, like I said, the highest frequency of interest in a telephone call is at 3,000 hertz. If we sample it at 8,000 hertz with 8 bits per sample, we would get a sampling rate of 64,000 bits per second, or 64K BPS. Like I mentioned a second ago, CD quality is 44,100 hertz per second, and it's usually 16 bits per sample. And then often you have stereo. So as you can see, there's going to be a lot more CD quality song recorded with stereo will take a lot more memory on the hard drive than a mono telephone call. So here we have some just kind of more explanation of what I just said there. Let's actually do a quick little demo. Why don't we? Let's do it. Let me grab our old friend, or maybe a new friend in this class. Let's just create a sample here. If I just, let me show you what I'm doing here. Let me go to audio. So I'm going to be sampling at 48,000 hertz. So it's going to take 48,000 samples per second as I record. off of my Elgato Wave 3. I'm going to be using one channel, so it's mono. Okay. Let's just do this real quick. Let's just try something. Here we go. Testing 1, 2, 3. Apple, banana, orange, mango, kiwi, strawberry, whatever. Okay. So let's see how long of a sample did I take. My sample is down at the bottom part of my screen. It says it's 4 seconds and 4.931 seconds. Okay. 4.931. I'm going to save this out to the hard drive as a wave. I'm going to come up here and go to export audio. And then go here. I'll just call this numbers and fruit. We're going to save it out. We're going to save it out as a 48,000 hertz, 16-bit PCM right there stands for wave. And we have mono, just one channel. Okay. Good. Export that. Awesome. Let's see if we can calculate without looking at how big it is. Let's just see if we can calculate how much storage it should take on my computer. Let's just open up a little spreadsheet. Let's zoom way in. Okay, so my sampling frequency was 48,000. Okay, and I was doing 16 bits, a bit rate, or excuse me, not bit rate, but what's it called? Bits per sample is what I'm trying to get to. Bits per sample was 16. I misspelled sample. That's all right. And number of channels is 1. Okay. The number of seconds I just said was 4.931. I think that was. Let me double check that real quick. Yeah, the bottom part of my screen, 4.931. Okay. And what else do we need here? Is that all we need? Let's see. Yeah, that's all we need there. So let's see if we can figure out how big this thing should be before we look at it. Let's come down here and just do equal sign. Let's take 48,000 hertz per second. Let's times it by 16 bits per sample. Times that by the number of channels, which is 1. Okay, and then times that by the number of seconds that we recorded. Okay, so I should have 3.787 bits. This is the number of bits and bits. Now, if we go over, let's pull over Visual Studio Code, and let me just clear that. Whoa. Sorry. Oh, I went into Vim there, sorry. Okay, sorry, I'm just trying to get out. Let's clear that. Let me zoom in for us right here. Okay. What I want to do is let's just look at what we have in here. I've zoomed too far in. Okay, so the number of fruits, it's saying that there are 400, no, what is that? All right. And then that's the number of bits, but the number of bytes, remember that? We had to divide that number right there, divided by 8. And it's saying that there should be 473,376 bytes. Is that the number I got there? Well, it's not exactly, but it's pretty close. And I assume it's because it kind of rounded the seconds right there. It says 479,084 bytes is what was stored when I saved out that WAV file. Anyways, that's how you calculate how much storage will take. It'll take audio file will take on your computer. Well, at least a WAV file. A WAV is uncompressed, like the full information's all there. There are other ways, other file formats. In fact, let's move on to that. There are other file formats that are compressed, or what I call compressed, and it takes less information. Let me just look at. I just simply want to see myself here to make sure everything looks good. Okay. Good. Yeah, there are different file formats. Like I mentioned, WAV. The WAV file format is uncompressed, like it's full. All the information's there, and so it's the biggest. Those files are the biggest because of that. And they often contain headers that can contain information about the file. There are other file formats I'm sure you're aware of, audio formats, MP3, right, ACC, and others. I have some down here. AIFF and others. NIST has one called Sphere. There are other sound files, OGG as well, and others here. Like I mentioned, Wave can give you information about it. So, yeah, it'll give you a header, has information about it, has just kind of metadata about it. If I actually come back over here, if I go back over to Visual Studio Code and I vim into numbers, fruits, wave, you can see here it's kind of messy, but here's the metadata. There's the RIFF right there. Wave format, it says wave FMT there. Anyway, this is a header on the actual file. That's what I had opened a second ago. Okay, good. I don't need to show you everything, but there is everything there. Okay. Yeah, so NIST. NIST stands for National Institute of Standards and Technologies. They have another file format called Sphere that we'll probably see this semester. Okay. There are different audio tools, conversion tools, SOX, FFmpeg, and there's an actual little, I think it's a Python function or a Python script that ships with Sphere files that you can use to translate or convert it into more common file formats. But FFmpeg right there, that second one is awesome. This is a really cool cross-platform little audio tool. It's a command line tool. I mean, it's not a program you click on and it brings a nice little GUI. It's a command line tool that you use to translate between or convert between different audio or even video files. And in fact, Audacity itself, Audacity uses FFmpeg under the hood. When you ask it to import some weird file, and it does, it's because of FFmpeg under the hood doing it. Okay. Good. Well, I think that's it. Yeah. So let's go back to this view. Go back to here. There you go. So what have we learned here? We've learned that sounds are just waves, just like water waves we can see in the ocean or in a lake or whatever, right? It's just simply waves of coming through air molecules. That's why in space, for example, I've never been to space myself, but I hear that, pun intended, that there's no sound. Like you can't hear in space because there are no air molecules for sound to travel through from the source to the receiver. Right, and so down here, it's just simply waves propagating through molecules, air molecules, perturbing them, and the frequency with which they arrive at the receiver affects the pitch. If it's a pure tone, for example, right, you're not going to hear pure tones in the wild. I don't know of any natural thing in the natural world that is a pure tone. The only thing I know that's a pure tone is a tuning fork, right? Anyway, so we'll talk more about complex waves and what formants are in speech, what partials are of sounds. But there you go. Thanks for watching. See you next time.